So none of this is going to be sexy and new stuff. I'm likely to sort of, it's all old hat really, but it's sort of trying to put a new spin on it. Here we go. So I'll go through, go back to basics and compare directed and constraint random verification techniques, and then go back to basics with a really simple example, and just to show you why we need to do constrained random verification. And then we'll go into just a simple bit, a few bits of code with some deliberate mistakes in them, to show you how you might put together your constraints and your in your sort of UVM environment to generate stimulus that you want. And then we'll go through some of the sort of methodology, the right mindset, and how we use UVM mixing. Going forward, there we go, it's very slow. So here's directed testing. So as it says, we're trying to go and identify all the scenarios we need to check the expected functionality. So this is the kind of thing which I see this quite regularly, where people start off with a story in the V plan. They'll say, well, we need to look at this, we need to provide this stimulus, then check that when we move on to this scenario. And it's very much a sort of story type scenario. So it relies upon you having a bunch of expected responses and a large suite of procedural tests. But the great, which sounds like it's a good methodology because it's quite easy to sort of generate that. It follows your thought process. But what it's not doing is it's not looking at the unexpected behavior of the design under test by definition. You're not exploring anything else. So you've got a very weak verification methodology. Thank you. With constrained random, what we're doing is the key word here is we're putting constraints on a random stimulus. We're not using utterly random stimulus patterns. So it's all nicely structured. We'll probably have a certain order in which we do things in the bring up of the design, the chip, whatever it is that we do. We'll probably do that in a very structured way, but we'll have some constraints which will control the random generation of the stimulus on that. Now, in order to make this work, it's actually a lot more work than the directed tests sort of set up. We need to go back a few. Don't know what's going forward, because we need some automation in here. So we need to have some automated independent checker, which is checking the output of the DUT to make sure it's actually doing what we expect it to do when we're imposing random stimulus on it. The key point here, which so many times people get wrong, is that the later, but stimulus, all of these concerns, the stimulus generation, the checking, and the coverage are all separate concerns. Let's go back one. So here's a really simple, I don't know why it keeps going backwards and forwards, but here's a really simple example. So this is a sort of mixed signal world. We've got two DC to DC buck converters here, which are providing power to 4 LDO regulators. So in this simple system, we've got some controllable LDO range, so 32 steps from 0.9 volts to 2.5 volts, whatever it might be. The DC to DC, the buck converters also have 32 steps, 1.2 to 4.4 volts, and those supply the regulators there. They're all going to be started up during this chip boot up process, and any DC to DC can supply one or more LDOs with this sort of switch mechanism here. So each one of these LDOs can choose who is going to provide it with power. One of the things that we always need to be conscious of is that each DC to DC converter has to have a headroom of at least 200 millivolts above the highest voltage selection on the LDO that it's actually supplying. The other thing we have in this system is we've got a scheduling system to schedule the startup order of all of these power converters. So we've got a 16-slot system, but we've also got a constraint here such that any of these buck converters needs to be started before the LDO is supplying is started. So there's obviously some ordering dependency on that. And then the voltage selection could be anything within the range. So very simple system, looks dead easy to verify. But if we go through the verification space required to look at that, just purely from a digital perspective, the number of configuration bits you need. If you think about the voltage selection we had, the LDOs have their configurations, their voltage selection times 4, and then the DC to DCs have we have 2 of those with 5 bits each. Then we've got slot sequencing. So if you add all the bits up there, you've got 2 to the power of 82 combinations. So even if we were able to sort of verify each of those to brute force through it at 100 megahertz will take I don't know, longer than it's taken since the Big Bang. Anyway, it's just a ridiculous amount of time. So we need to forget about scenario-based or exhaustive testing. It's just never going to happen. So then we move on to the concept of constraint random verification. So this is the sort of what's known as the spray and pray approach. So we're throwing loads of darts at the dartboard and hoping we get lucky and we hit a bug. So, and we're also using the concept of the fact that we've now got these compute farms and we've got a huge amount of CPU horsepower and licenses, hopefully, to actually run these random test scenarios. But to do it completely randomly doesn't make sense, because we want to progress through the design scenario space in a sensible manner. Albeit we do want to introduce some outliers and things that will show up some corner cases where the design doesn't behave. So we would have something like a bunch of constraints for our constraint solver built into our simulator. That then will solve all the constraints, or tell us if there's some violations, there's some constraints which don't resolve, and that feeds into a random number generator, which then generates our stimulus values. But what we also need to do is we need to measure the scenarios that we're actually hitting with a functional coverage model. So here's how we might model our stimulus space or configuration space using some UVM or some system Verilog here. So each one of those different rail modules we saw in the previous slide. So each one of these blocks here, we consider it to be a rail. We've got 6 of them there. And we would have a configuration object declared as a UVM object for each one of those. So we'd have an ID, we'd have a supply selection. So all of these are ints, but we'll obviously constrain the range down later on. So that's a supply that's going to be supplying this rail. That's the V-cell value it's going to be set up to be, and that's the time slot it's going to be switched on at. So first of all, we can apply some constraints to those to say, well, the V-cell range is going to be inside 0 to 31. We said that there was going to be 32 steps for all of those. So that's a common constraint we can apply to all of them. And another one is that the slot has to be inside 0 to 15, 16 slots. So that's common for all of the rails. So we have that rail configuration, but for our system, we've got 6 rails in it. So if we then create a class, which is another UVM object, in which we simply instantiate a dynamic array of rails in it. Okay, well, we know in this example we need 6, but we could make it completely dynamic. We have another number in here, which again is random, which specifies the number of rails. So what we would do is constrain that to be 6 in this particular example. And then if we use that to control the number of rails in this, and we have a special constraint here to say that we constrain rails.size, that's the size of that dynamic array, to be equal to the num rails. If we randomize this object, we randomize with the constraint to make num rails 6. What it does is it's basically like saying do a new of 6 on that when we randomize it. It gives us 6.
Well, you randomise it if it's going to be 6.
Well, that's true. We don't. I just wanted to show you how we use this in a general sense. Yeah.
When we build a chip, we randomise each time how many DC converters you get.
That's what I think. True. I'll take that one. But if we randomize this, what we do is we'll get an array of 6 or n, rails, but there'll be just handles to this. There will be nothing inside it. So we have to, unfortunately, use a special trick for that. And that is that, if you see on this slide, we've got this hook method called post-randomize. So that says after we've called randomize on this class, previous one here, this guy here, the sysconfig, after we've called randomize, let's actually populate each one of those rails with some information, some data. Let's solve it again. Let's randomize them again. And we'll go around that loop with a for each loop. First of all, we'll do a new. So we create a new UVM object for each one of those rails configurations. We set the ID to be the index in the loop. And then we'll randomize each one of those, rails I randomize, with these inline constraints. So first of all, we have this constraint ordering. So we need to solve the supply selection before we solve vcell. The reason we need to do that is because we've got this business about the headroom we need. So we need to know who we're supplied by. We need to solve that variable first so that we can apply the constraint for vcell later on. So that's called an ordering constraint, where you solve one thing before another. The second thing we do is that for any of the rails from 2 onwards, we need to then, we don't care about rails 0 and 1. They're the DC to DC converters in this scheme of things. So anything which is greater than 1 from 2 onwards, we need to say, okay, well, we supply a constraint to say that its supply is either 0 or 1. That means DC to DC converter 0 or 1, buck 0, buck 1. And then we have another constraint to say that the V cell of any of these LDOs has to be less than its supply, the V cell of the guy that's supplying it plus 2. So it's got headroom 200 millivolts. So that's your headroom constraint.
So and then V cell is in steps of 100 millivolts.
Yes, that's right. Yeah, for those ones, I think it's a different scale for the LDOs and the DC to DCs, isn't it? But and then the final constraint we have here is that we need to say, okay, well, given the DC to DC converter it's got a slot in which it switches on, we've got to turn on in a slot after that because we can't turn on before our supply is turned on. So we say that the slot for the rails I that we're at the moment has to be, greater than the rails its supply. So that's the index into the rail which is supplying me at the moment has to be greater than that.
That's assuming your customer tells you can do that.
Assuming the customer tells you to do that. But I did actually bang this into the slide and then put it into the simulator, and I got some constraint violations in it. And maybe you could see if you had eagle eyes what might happen here. The fact is that if any of these guys here, if the slots which are supplying, the rails which are supplying these guys here are on slot 15, then you can't have a value greater than 15. So you'll get a constraint violation because on a previous constraint, I said the slot can't be greater than 15. So the simulator will say, can't do this, mate. So a simple way around that is to say any of these guys here, the DC to DC converters cannot be in a slot greater than 14. Yeah. So at least everything else after them would have to be in the next slot. So if we run that through, we can see something like that output there where we can get UVM to do some nice console output like that. And then we can run through our simulations and pick up the coverage with our vManager tool. But the points to mention on this is that although we might have quite a powerful way of generating stimulus, it doesn't do anything to reduce the verification space. So what we're trying to do is we're trying to say, well, it's up to us to create a metrics model and look at the interesting scenarios that we need to cover. And then hopefully we hit some other things where we weren't expecting to find a bug, but we find a bug. One of the good, so we create a metrics model based upon what we need to cover in the spec. So that's all the stuff that you get in your V plan. Another thing you can think about is pairwise crosses between features is a useful strategy to have in general. So you've got multiple things going on in your system or your subsystem. It's good to cross activity between two, combinations of pairs because it's statistically likely that you'll get bugs when you've got two things interacting. So one of the pushback we get from our teams internally is that, well, we don't want to run all these constrained random simulations because our AMS simulations take days, so we can't do this. It doesn't make any sense to us. What you can do, though, is if you've got a common verification platform where you can run the same tests on DMS that you can on AMS, is you can run your regression suite with the DMS in a fast mode, with the constrained random stimulus that you generated, with your coverage in place. Then what you do is you look at the functional or code coverage and you rank the tests according to their optimal coverage that you're getting. So you've got some scenario coverage, some part of the V plan you want to look at in AMS, then you get those tests and you can basically use the ranking which is available in the tool to identify the best tests to run under the tortoises in the slow AMS environment. So you can sort of cherry pick, but it only works if you can seamlessly run those test scenarios between those two different verification platforms. Fortunately, in Renesas, we've got that, so we can do that.
It was also presented at DP Club 3 years ago.
Right. So one thing that we need to keep telling people, hopefully this is very apparent to everybody that's in the verification conference here, is that whenever you look at V plans, that it's so important to keep all of these different pillars of verification as separate and equal concerns. So the stimulus, we talked about the stimulus today, exercise the way of designing in ways we haven't thought about. That's what constrained random does. Checking is there always for all tests, automatically checking the expected behavior, and the coverage is there to measure what you've actually done. And all of those are as important as each other. You can't have coverage without the checks in place. It's meaningless. So yeah, it's something that we have to keep repeating to people to get the right kind of methodology. And also in terms of the mindset, the metric-driven mindset is not to think about, well, we need to get all these test cases to pass. We need to find some bugs in this design, which are almost certainly going to be in there. We never see any bug-free designs. In fact, I've sort of got a record, I've got a little file of bug escapes or bugs that were found post silicon or close to tape out, and almost all of them you could sort of categorize as being things that were due to over constraints in the verification environment, the things that the test cases couldn't possibly find them because there was too many fixed delays or there was too much procedural action going on inside the stimulus, so that you would never cover those corners. So we need to be looking for the bugs that we know that are going to be in the design. I think I've mentioned it. Final slide is to just discuss UVM mixed signal. So UVM mixed signal is supposed to be a standardization activity, which Peter mentioned earlier, which hopefully there'll be some kind of white paper or first release early, end of this year, Q3. But the idea behind UVM-MS is to basically allow constrained random verification with these three pillars of stimulus, checking coverage, and a standard way of doing it to be extended into the mixed signal space. So it addresses those things about the optimal partition of verification code between the different engines, the co-simulation of the analog solver and the digital event-driven engine, and where to write the different parts of your environment for the most portability and reuse between AMS and DMS. It's built upon expertise from UVM and the AMS fields. So yeah, it's to allow you to do all that, apply the good metric-driven verification for all of those things that you need to do in the mixed signal domain. So the conclusion is that constrained random verification is applicable to mixed signal designs, but you don't get something for nothing. You've got to use more effort in terms of your checks. You've got to put coverage in there. But you can, if you've got a reuse methodology, if you do it in the right kind of way, it can pay off between, block to top or chip to chip. It can work quite well, as long as you have to spend a little bit of time thinking about reusing it and building it into your code base. And then another lesson is that if you have a co-verification platform or common verification platform, you can basically run things in DMS first and then choose the best tests to run on the slower AMS platform. I think that's the last slide for me. So are there any questions?
I'll ask an easy question first. The first one, so do you think that mixed signal engineers should adopt UVM, or should those that are already trained actually in UVM should adopt mixed signal?
That's difficult.
That's an easy question.
Yeah, wait for that.
From my perspective, I would like to see more people who are holistic verification people, put it that way. We have a few of them in the company, not nearly enough, who aren't necessarily pigeonholed as mixed signal verification engineers, who aren't phased by just negating what Peter said earlier about he doesn't touch anything in UVM. Actually, that's not true because he's very capable and he could do. But we have a certain number of people who can handle that stuff. I mean, obviously, where we don't handle that, what we try to do, I mean, UVM itself is supposed to be a layered type of architecture where you have a certain level of sort of abstraction for those that are writing the environment. So they're more the kind of nuts and bolts people that are writing the UVCs and the environment, how it came together. And you've got a certain level above that where that's where the test writers.
But if you take this as an example, you've got a shared environment, DMS and AMS, you can feel a digital verification guy who's an expert in UVM and constraints to write the whole lot for you, and you go and run the AMS ones because you know what to look for. I mean, and that's what we have done. We've had some graduates come in who've written very good self-checking stuff for ADCs and then literally just run it in AMS, just a handful in AMS. So, yeah, I mean, I still do directed testing in AMS if I'm asked to do anything. But the younger guys can now do all this class-based stuff and randomize. I need to know what I'm doing because I'll be on the phone to Cadence probably for some other issue.
I think for a good, if somebody's written a UVM environment and the sort of test layer in a good way, particularly if they've got you've got common sort of base test, which does a lot of stuff for you, like randomizes the setup and all the rest of it. So you're already getting that goodness from the start. And then you can, even if you wrote this, it says if you write some directed sort of little scenarios, you've already got something there which is adding a little bit of value, to what you've got. And the fact that you have more communication between the verification teams, let's say, and if you're using that common platform, that means that you're sharing stuff a lot more. But I totally get what you're saying that we'll probably never get some of the AMS guys to be.
I think the sort of this is to have your verification, whoever's doing verification, think like the verification engineer, not to think like a designer.
Yeah.
It's really just thinking about the what could go wrong, and not just to go to just assuming it's going to work.
Yeah.
So and again, this I think really helps in terms of trying to explore the cases that you haven't thought of.
Well, I was going to say, do you want to go online? Is anyone online? Last question.
Any questions online? Nobody's online.
I guess
There are people online.
Oh, sorry. Apologies to those
But
online.
there are no questions.
Okay.
I guess the hard question would be, so you're using your constrained random verification in a DMS or sort of at the DMS scope level to kind of give us the cream of what is the best case scenarios to run in the slow simulator.
Yeah.
Does that ever perform actually bring any surprises that this is something that someone writing a directed test, Peter say, couldn't have come up with himself?
I think the point there is, well, maybe what you're looking for there is that you're looking for good coverage. It depends how you rank it, right? Depends what you're looking at. But if you're looking at coverage of, say, A to D interaction, which is probably what you want to focus on when you're looking at AMS stuff, where you want to invoke the co-simulation, then you can target in, focus in, and create coverage either structurally or with functional coverage, and say, this test is really hammering that ATD interface. So I'm going to pick that one for the AMS simulation. So I think it's just a question of having a bit of feedback and, sort of a bit more scientific feedback, really.
Yeah, I think
But you might get
it sounds often like Brad, you would just threw it in, just change the net list abstraction to schematic and threw it in. Probably we should have analysed the data first, but hey, again, it's all constrained random. We might have been lucky by just running another seed and hit that one bug where.
Just one question online. Can I just throw that one in? Is this showing that first DMS must be run, then AMS?
I think it is for the ranking. Yes, I would say so. Yeah, you have to do that. And typically we do that anyway to pipe clean the test to make sure, because you don't want to find any sort of null pointers, if you're going in UVM in an AMS simulation, just run a couple of days.
It's better to do that quickly. Tests quickly.
Yeah. So
Are you intending for this so that we can use UVM, do full Monte Carlo style analog simulation of the analog designs, including noise, sensitivity, all that other good stuff?
I think not. You could do it. You could do it at block level if it's a small block.
Yeah.
The analog simulation times are, in say a 10-minute window, but you wouldn't do this at the chip level.
No, and I find that the full analog behavior is still best solved with the analog verification environments and qualification of models against analog.
Yeah, what we tend to find though is that normally at the block level, because of the way most of them draw their analog test benches with PWL steps, they haven't tested every combination. So we in the past have done versus schematic again presented at CDN9. Go and grab the papers from there. Is that we took an LGO that we'd sold 100 million on. And we went and tested all the combinations overnight and found there was a test mode, and if you did this at the same time, you hit an issue. So this is the sort of thing that maybe you could do at block level.
So it's testing that crossover between the digital control part, if you like, of an analog block.
Yeah.
Rather than its full raw analog performance.
Yeah.
It's dangerous if you did Monte Carlo with this as well. You've got the explosion of simulation.
Yeah.
That's really not going to be feasible. So, because you've got two different randomizations going on, that's a big search basically.
Yeah, I know that's degree of freedom.
Yeah. That's the end of it.
thank you.
Thank you very much.
I'll give you a